on here?
Yeah. Hi, can you hear me? All right, hello everyone, welcome back. I have you for 75 more minutes, and I'm excited about that. There was this great question at the end of last lecture, which was sort of trying to get at sort of the utility of my way of presenting things here, which is a good thing. And I thought a little bit more about it. I wanted to sort of say clearly, on one hand, I'm trying to give you a very general theoretical edifice that expressivity and statistics and dynamics are really central to any theoretical understanding of machine learning, at least at a neural network level. But that answer is kind of like telling you that quantum field theory exists and not telling you why you should care about quantum field theory, like standard model, condensed matter systems, et cetera. So in many data systems, we actually want to train the networks. And in fact, we might train many, many, many of them to try to see which one performs best and compute the variance. That's some of the relevance of the statistics. But the dynamics, of course, is absolutely crucial there, because if we don't train the network, it's not doing anything useful for us, unless we guessed really lucky. You could have just randomly picked the right point in parameter space. There's this whole thing that's sort of related called the lottery ticket hypothesis. How do you, yeah, anyways. That's a whole field of ML from maybe 5 years ago. But another practical thing that I didn't emphasize last time, which is a kind of a dirty word in academia, is money. And not money necessarily in the sense of people doing ML making it, which is what they're doing. But one of my friends that came up with some of the stuff related to this pillar here And we've already seen the importance of scaling in the system, that there's this hyperparameter n, and as you scale, different things happen. And if you don't choose n wisely in terms of like a normalization, your 2-point function can blow up and your variance can be infinite, which sounds really bad. And it is bad. But so this friend of mine, I'll tell you the story. I actually just reached out to him this morning to try to get a dollar figure for you. He works at XAI now. I met him at Microsoft Research, and some of the stories I'm telling you about today about Gaussianity and field theory, I learned at a meeting that he and I, with some friends, ran at Microsoft Research in 2019. One of the questions that's essential in machine learning, you often, in practice, have a network, and you train it. And there are these things called hyperparameters. Hyperparameters are parameters that you don't train. They're parameters that like you choose at the beginning. So one hyperparameter could be the width. Another could be the variance of the initialization distributions, and so on and so forth. And so in practice, what you do is that you try a bunch of different hyperparameters. Maybe you do some sort of box scan over the space of potential hyperparameters. So that sort of box scan over hyperparameters can be rather costly in terms of compute, and rather costly in terms of compute can be rather costly in terms of money. So one of the things that was motivating for him as he was finishing his time at Microsoft Research and moving on to XAI was to think about the question, if I do a hyperparameter scan for a small model, for like a small enough neural network, you're not hoping that it's going to be the best thing in the world, you're just hoping it's going to train. Ideally, what you would like to be able to do is do your box scan for simple models, which costs low compute and therefore low money, and then take the hyperparameters and have the optimal hyperparameters for small models also be good hyperparameters for big models. So this is something that's happening in large language models now. There's a couple of different sorts of frameworks for thinking about this scaling up. The essential question is, how do you scale up your models without having to do huge searches across model space? Because the current iteration of large language models, each time you sort of train a new GPT-4 or a Grok or a Claude, et cetera, we're talking order $1 billion, okay? And so the procedure, the number that he gave me is that this clever scaling up in any one of these situations might be a 5 or 10% effect on that $1 billion training run. And so these ways of thinking theoretically about neural networks and how you can scale up and preserve performance as you scale up without having to research in the big model space is actually really important. So it's practical for like good training. It's practical because there's this edifice that I'm trying to give you. But it's also practical because the companies are trying to achieve good things without having to train an enormous number of LLMs. They want to choose wisely. And one way that they choose wisely is they start with small models and they scale up. OK, so anyways, just wanted to mention that because the question was so good. And I forgot, because I'm a physicist and I don't usually think about such things, that in industry, people are concerned with saving their company's money, OK? So the TLDR is CS is historic, ML is now, and ML theory contains but is not equal to neural network theory. Everything I've been telling you about has to do with neural network theory. The first pillar is expressivity. How powerful is your neural network? And there are theorems that tell you that basically, for certain types of neural networks, somewhere in their parameter space, there is a function that can approximate sort of any arbitrary function. But that point may be over here, and your draw at initialization may put you in parameter space over here. And if you redraw, it might put you there, and it may put you there. So there's some density on parameters at initialization, which means that you want to understand the statistics. But as each one of those neural networks trains, there's some trajectory in parameter space. So you can sort of think both of the trajectory of an individual neural network as it moves through its parameter space during training. But you could also say, I have this initialization density. How does that density move as training occurs? And as that density converges in training of many, many neural networks with a density on parameters moving through parameter space, what is the expected prediction or 1-point function? What is the expected covariance? What is the covariance of the model, which is related to the 2-point function, or more specifically, the connected 2-point function? So I think that these are pretty relevant in general. And in practice, some of these ideas are actually having impact on what's happening in sort of large-scale large language models. OK? I think that's it. So what I'm going to do today, so in the notes, the derivations in this part are actually probably too intense to go through in lecture in the interest of time. But luckily, there are real concepts and principles there that I can just tell you what they are and then tell you what the results are. And we'll see where I get to. Depending on where timing is, I might tell you about more general connections between field theory and this story. But I'm going to spend most of the time today talking about actual neural network dynamics. OK? So with that in mind, that is my first page, which is not where I'm beginning. OK, let's finally talk about dynamics. And there are many, the dynamical question is based on what you're trying to do, like learn language or tag jets or label dogs or whatever. How do you update your parameters? What is your algorithm for updating parameters to realize that trajectory through parameter space that gives you a good neural network? That's a dynamical question, and there are many algorithms for updating your parameters. That's a whole field. We're going to take the simplest today and ask the question, how does a neural network evolve under gradient descent? OK? And that will lead us to something called the neural tangent kernel. And I will present a solvable model of the neural tangent kernel. And I will tell you ways in which that model is bad. Toy models aren't always good. Toy models can teach us things even if they're bad. This is one of them. And in certain regards, it is good, but in others, it's bad. And we'll talk about that. And then we'll move on to feature learning. But the question is, how does a neural network evolve under gradient descent? OK, so we start with, and I will not do quite so much with my labels y alpha. I'm trying to be good about not using y alpha in other contexts in this lecture, or y in other contexts, but apologies if I do. It'll hopefully be clear if there's a y that is not this y. So I just have a bunch of inputs and outputs. In a physics context, some sort of image of something happening at the LHC or other related data, whether the associated jet is a quark jet or a gluon jet. People here can tell you much more about that story. But there's inputs and there's outputs. This is the input to the neural network. And you're trying to get the prediction of the neural network to match onto the known output. OK? So if your neural network labels a dog image cat bad, and you want to penalize it and update it so that it starts predicting dog on those images. OK, so with that in mind, our loss function in this supervised setup, this type of thing is called supervised learning. This is a loss function. I'll sum over the data, script d, alpha equals 1 to d. And there will be an element-wise loss that depends on the neural network prediction on the input and how that compares to the associated output. So there's some notion of bad for each pair of data points, x and y, and how the neural network prediction matches onto that. And then we sum over all the notions of badness and goodness, and this is the overall loss. We will optimize by gradient descent. Which is the update. You need an update equation for your parameters. D theta I by dt is minus eta gradient with respect to parameters of the loss. And of course, the loss depends on the neural network and the data. OK. This is where you might write many other things on the right-hand side. Now, in practice, we are, in general, on the computers, we are not actually doing differential equations. We're doing finite difference methods for updating your finite difference methods versions of the diffie-Qs. For theoretical reasons in this limit, we will be doing continuum time gradient descent. This is a situation where you can think of this learning rate as being very, very, very small, and so you can use calculus. OK, so this is the continuum approximation of what in practice happens on computers. It's the normal thing we run into when we do diffie-Qs numerically, right? OK, all right. It's also convenient to define some other object here, delta of x, which is dl phi of x, y by d phi of x. Okay. And with this way of writing things, you can also write gradient descent in this way, which is eta over d, sum alpha equals 1 to d, delta of x alpha, d phi x alpha by d theta I. what is this? This is this equation here. I do a chain rule, and I trade the d by d theta. So this now is dl by d phi by d theta. And so I basically just used the chain rule to relate the function space and the parameter space in this way. So this is a canonical thing that is done. So this is just a different expression, but it's a one-line step from here to here to get a different expression for gradient descent. OK. Time for a classic result. This is something called a neural tangent kernel. OK, so I take that equation, and I, instead of asking about how the parameters update, I instead want to ask the question about how the function itself updates. So what I'm interested in is d phi of x by dt. Yes. But d phi of x by dt, Einstein's summation here, is d phi of x. Maybe I'll write it as a partial derivative. D theta I by dt. And sum on I. And now I'll use, this is just a general equation. And for different optimization algorithms, you might take a different next step. But I'm going to take gradient descent. And I'm going to use my gradient descent equation and write the next step in this update. And what I get is eta over d sum alpha equals 1 to d delta x alpha theta of x alpha. And at this point, it's actually worth pointing out that x, it could be any x in the domain. These alphas here are specifically the things that these x alphas are specifically the ones that I'm going to be training on. So this is some sort of object, if you like, that communicates between the things you're training on and the things that you're testing on. We'll talk a lot about what this object is. This object, I didn't write down what it is. This object phi of x alpha is equal to d phi by d theta I, d phi, of x alpha, d theta I. And this thing has a name. This is, different people call it different things, but this is the neural tangent kernel. There's a naming thing. Some people call this the empirical neural tangent kernel. And then the thing that I will call the frozen neural tangent kernel, they call the neural tangent kernel. But let's just talk about what this thing is. This is a fundamental object that arose by doing like 3 equations. Yes?
What is delta of xa in that?
It's this.
Equation? Oh, OK.
Yes. Yeah. So this tells you, let's talk about what this equation means. This says you're gonna train your network, and the network is gonna be updated. It's gonna feel how the loss fluctuates as the function fluctuates. That's what this is, right? And then how that loss fluctuates as the function fluctuates gets sort of propagated from points alpha to points x via this object here that is this foundational thing called the neural tangent kernel. And this is a result from NeurIPS 2018, I think. Very fundamental, and this was, for a long time, my favorite example of why there's a lot to do in ML theory, because it's a very fundamental thing that was discovered not so long ago. And when I first learned about it, it was 2019. So let's talk about this, because this is a fundamental thing that is arising. And I'd like to make some points why right now, for now at least, this is a terrible object to deal with. So on the one hand, it's fundamental, because I got at it by a couple of equations, and we can sort of understand that it's communicating information on test points, on train points to test points. But it's terrible in a number of reasons. One is because it is parameter dependent. OK. This sum, this Einstein summation, is a sum over all of the parameters in the neural network. And one of the most famous open source large language models is out of Meta. It's called Llama 3, and it has 70 billion parameters. So this is a sum over 70 billion things, okay? So that's kind of nasty. It depends on parameters. But it sort of gets worse because the parameters in general depend on time. So in general, for finite networks, if you studied this thing at initialization and you computed it across all 70 billion parameters for llama 3, you would then have to go and track how it changes in time, which is also hard. So it's sort of getting worse. And the third thing is that it's stochastic in the sense that because the neural network starts at initialization at some random point, it picks up the stochasticity of the random draw because that's the initial, that determines the initial parameters that appear in here. And these are some of the reasons why it's terrible to use. For what it's worth, this actually isn't so much of a problem. It's non-local, which is usually something that scares us in physics, but it's not so bad here. And as I mentioned, sort of theoretically, what it's doing is that I'm asking how the predictions on test points update over time. X is not necessarily in the training data. And this is the function that communicates what's happening at test points, at train points to test points. So theoretically, it's very nice, but in practice, it's terrible to use. OK. Any questions?
What was the result of 2018? Just that you can write consent in terms of this hard-to-use object?
I'm about to tell you why it's classic. Right, so this is not the end of their story. The thing that's classic about it is that it's classic because of a simplification. And this is one of the major ML theory results from the last 10 years. And certainly in 2018, this was one of the things that everyone was talking about. So a fact that I'll tell you that is justified by some calculations later in my notes is that in the n goes to infinity limit, this is any of the n's we were talking about yesterday. It's some large infinitely parameterized limit. The neural network is in something called the lazy regime. And what that means is that, sorry, that's theta of 0, is that, and is much, much less than 1. It means that where the network starts in parameter space, the whole trajectory for all of time sort of lives in a little local neighborhood. So for llama, you're in this 70 billion dimensional space. And you start at one point. But as the network becomes really big, OK, it does actually arise in transformers, not necessarily llama. But in cases that have this behavior, which includes a lot of different models, things just don't move much. The entire trajectory of the neural network through parameter space lives in a little local neighborhood of where it started. And you might say that the neural network was lazy. Okay, this is the lazy regime. So there's a reason that this is relevant, the lazy regime. In the lazy regime, if the parameters don't move much, then in the limit that n goes to infinity, the prediction of the neural network is about equal to that of the linearized model, which is defined to be the initial parameters, phi of the initial parameters at x. It's the first order Taylor expansion. Okay. And I've truncated it first order. So I note that this linearized model that I write down is not necessarily linear in inputs. It's not like a linear function. It's linear in parameters. And this is a justified approximation because people have shown in many different ways that many types of neural networks, when they become big, they don't move so much, and their dynamics is effectively described by a linear model. Yeah?
Do you need to make any assumptions on how you sample the initial weights?
Yes. So basically, we'll talk in a simple derivation. I'll show you sort of. Yeah, you need things to be well behaved enough, such that and well behaved with respect to the choices of initializations for weights, such that when you study the details of what's happening, you can see certain 1/n suppression in how the thetas are updating. You could imagine studying, as a theorist, how much in general are my thetas updating and how does it scale with n? And if it scales like n to a negative power, it's not updating, it's not moving very much, and that's the essence of the result. And it does depend on the initialization. But many neural networks have this sort of limit where this is true. And in particular, the ones I showed you yesterday do. Deep feed-forward networks have this, CNNs have it, attention has it. And similarly, just as NNGP, this Gaussian thing, holds for many, many architectures, this also does. OK, so the reason that this is a nice limit is that, I'll write it up here. It's nice because if you take the NTK of the true model in the limit that n goes to infinity, like of the full neural network, it's in this linearized regime. Well, if I look at this, remember this NTK is taking parameter derivatives. And if I take parameter derivatives of this, it's just picking off this term. And then it's doing it twice, because it's d phi of x by d theta I, d phi of x alpha by d theta I. So it sort of picks up 2 copies of this. And what this thing actually is the NTK at initialization. Okay. So this is one nice feature, that because the model becomes linearized at large n, this general object that is time dependent, the parameters don't move very much, so the NTK doesn't feel its update. And literally, the NTK becomes the NTK at initialization. So this sort of gets rid of one of my terrible to use aspects up there. Yes?
Maybe you're going to say this, but it seems like it could be bad if you don't move enough in parameter space to find the point that you want to find.
Yeah. We will solve the model, and then we'll talk about why we don't sort of like it. Sometimes it can do well, sometimes it can't. One thing, you're worried about not moving too much in parameter space. I forget who said it.
This big space of thetas.
Yeah.
I sample some of them, and I just fill in these tiny balls.
And you have bad performance. Exactly.
And I never get where I want to get.
Exactly. So that is a valid concern. This is the limit that the dimension of the parameter space is going to infinity, though. And so a local neighborhood in an infinite dimensional space still has a lot of room to move and can still give you a lot of variance in the functional predictions. There's some famous ML person had some glib statement about that at some point, like local neighborhoods are big in infinite dimensional spaces or something like that.
Like, even though the best approximation might be way over there, we can still find a very good one in a local neighborhood?
You can find a pretty good one in a local neighborhood, but one of the problems is something called generalization. That in the solvable model, we'll see that this toy model can get perfect predictions on trained data, and then we'll analyze what happens with the test data, and we'll sort of see why it doesn't really make us as happy as we might wish. But the answer to Oliver's question, which is, well, maybe the good point is really, really far away, it's a valid concern, but I'm also pointing out that this is a local neighborhood in a very large dimensional space. So there's a lot of room to hide in a very large dimensional space. OK, so this thing gets rid of the time dependence. Where was I going? OK, and I'm going to show it to you in an example, the next bit. That's simplification 1, nice thing 1. Now I'll tell you nice thing 2. Nice thing 2, that is also very often the case, is that in the limit that n goes to infinity, when you actually do the calculation of this thing, now this thing tells you that you can just focus on the thing at initialization because the NTK isn't updating much during training. And I compute it at initialization. And what I get in many cases is that you can see that this object is summing over many things that are identically distributed and independently distributed. And so by the law of large numbers, which tells you that you can take a finite number of samples, take the number large, and if they're IID, you can replace it by an expectation value. You get an expectation value here of some b of p theta of x comma x prime, where the expectation is over whatever the parameters that are appearing. But the reason that this is nice is because now this expectation value is doing an integral over the parameters. So this tells me it's not time dependent anymore. And this tells me that in this large n limit, I can replace what is effectively a Monte Carlo estimate by an expectation value, I can integrate over the parameters, and I can end up with just some function. And it's in these lectures, I'm calling this thing theta bar for average of x prime. And the reason that this is relevant is that in certain cases, you can just compute that. Once and for all at initialization, it depends on the choice of parameter distribution that you integrate against in the expectation. But at the end of the day, when you do the computation, you just have some function. And in this case, I'm getting a little turned around in my notes. In this case, with these two assumptions, nice thing 1 and nice thing 2, the dynamic simplifies to be of this form. Where now this thing in this particular limit is no longer parameter dependent, and therefore it doesn't depend on the initial point in parameters. And it's not time dependent either. So it's just some fixed function, and I just have some differential equation for how the neural network evolves in time in terms of some very nice object. Okay? And you can talk about, do we like what this very nice object gives us? A toy model is not necessarily useful for things. It could be a spherical cow with no application to anything, right? But that's the simplification. Let me see. Good. Good. I will invite you to complain. Who likes this dynamics for a neural network evolution? I guess I told you that you should complain. I'll get my water while you answer. Sorry, can you speak up? Yes, but I can think this is a functional derivative of the loss. Yeah, the question was, it was pointing out that because this thing is evolving, there's sort of some time dependence in here. But we're going to treat this as a functional derivative of the loss with respect to phi. So it will depend on the evolving neural network prediction through here. But what I'm really getting at is that this object is not time evolving at all. And I'm inviting you to complain about that. Yeah?
Understand how nice 1 is thinking so that this kernel doesn't change as we train?
Yeah.
From one fixed starting point.
Yeah.
But I'm not understanding how we can use one function no matter where we set it from.
Oh, yes. Because the question is, why is it the same function regardless of where you start? And because when you do this calculation and you sum things up and you apply the law of large numbers, there's just many, many, many parameters appearing. And so you can interpret the whole thing as, I mean, you're in an infinite dimensional parameter space, and you can reinterpret it as an expectation value. So that one point in parameter space gets reinterpreted as a sum over a statistical ensemble. But the thing that you'll get is the same statistical ensemble regardless of where you start. And so it's the same neural tangent kernel for all. I don't know if that helped answer your question, because it's kind of a technical answer, but it is true. And it's not the complaint I'm inviting you to make. It's a very important technical point, but I'm asking you to complain about something else. Yeah?
Well, if the predictions are updated over time, how does the network learn?
Yeah. The predictions do update over time, but I'd like to talk, the network, you're basically saying the network doesn't really seem to learn. And let's unpack that. The network prediction is updating over time according to this equation, but this thing is fixed. And the only appearance on the right-hand side of the test point where you're trying to make your prediction, so you give it a jet image that it hasn't seen before, and you're hoping it makes a good prediction, it's right there. And so there's this sum. Imagine that there's data in this room, and there's the sum over the data in this room at the various little localized points. And there's little loss fluctuations as the function fluctuates as it learns at those points. But where I am is not one of the points that's being trained on. And this equation is telling me that I collect information from what's happening at all of those little points. But the way that it gets communicated to me is by something that is fixed and intrinsic to the neural network architecture at initialization with no sort of learning in the traditional sense. In some cases, this is just some fixed function. I know of a case where this is literally a Gaussian between x and x alpha. And so this doesn't seem to be what we would normally mean by neural network learning, because something that is fixed for all times at initialization and therefore doesn't know about the neural network learning is the thing that's communicating from train points to test points. And so when it's sort of like doing some sort of interpolation or average over all of the train data according to the weight of this function. Okay. So that's exactly the right point, that in some sense the network isn't learning in the way that we would normally mean. This object is too fixed. This object that communicates from training data to test data. Yeah? Yes. It is an interpolation. I like this picture of the data all over the room. There's all these points, but I'm not a trained data point. And so I pick up influence from all of that training data in the room, and you can make a prediction at me according to this equation. But the method of communicating between the test points and the train points is just some fixed function, which you can sort of see the theoretical drawback. Okay?
So how is there any communication between the test points and training points, whether or not this function is fixed?
Sorry, this is literally a function that depends on the train points and the test point. This is the function that relates them. It depends on x and x alpha. It's a kernel that's like, this is called it's called a neural tangent kernel. It's something that's like, in one case it's literally a Gaussian, and how much suppression you get there in communicating from one point to another depends on the distance, the exponential suppression of the distance between the 2 points. Yeah. Okay. All right. Cool. So, so we say that this thing doesn't learn features. Don't maybe harp on the feature part of it now. In some sense, you can just say that this isn't learning in the way that we would normally mean, because some fixed function is interpolating between the train data and the test data. Okay. I lost my point in my notes here. I think this is the new one. Okay. Good. So I want to show you this bit in one little case. Oh, I have another board. Okay. So in an example, I'll just take a single layer network with bias turned off for the sake of simplicity. And I'll try to be a little explicit about the sums because they matter. And in a minute, we will employ the method of staring. OK, so what is this? This is sum on I, d phi by dw1, I of x, d phi of x prime by dwi1, plus sum on ij. Okay. This is literally the definition of the NTK. I'm just summing over the two different types of parameters and taking tons of derivatives. Okay. And you can do a little calculation. I invite you to do it. Not now. I equals 1 to n. And what you get is this. Sum JL equals 1 to d, sigma of wij of 0, xk. Sorry, that's xj, not xk. Sigma w0 il xl plus sum from j equals 1 to d of sum on, of xj, xj prime. I totally, this is the definition of the network. Here's, I'm computing the NTK. I totally skipped something. So that probably looked totally crazy. Apologies. It was probably the worst mistake I've made yet. This is the definition of the network. The definition of the NTK is over there. I'm literally plugging that equation into the definition over there. I'm getting things that are quadratic in networks summed over parameters. And there's this hard cut here. These are different equations. And so I'm just continuing the calculation. AI, sigma. Like a lot of ML theory is thinking hard and keeping track of indices very carefully, which is also a lot of theoretical physics. Yeah. OK, so here's the full expression. OK, and I will define this to be 1 on n sum I beta I of x prime. OK, and so I have this beta I of x prime here. And if you look at what this beta I is, and you imply the method of staring, the I index that it picks up here, is feeling what's happening in this part of the weight, right? But the weights, I forgot to say, I'm drawing my weights IID. And basically what's happening is that because this I is picking up its I-ness through the ith part of the weights, what's happening is that it's filtering into the beta I, and the beta I's themselves as objects are IID. So this is a sum. This is 1 over n on a sum times a bunch of samples of beta I type objects, which means that this theta bar, x prime, Rikab, I see you. In the limit that n goes to infinity, this is the definition of it, this becomes, by the law of large numbers, replaceable by an expectation value, which just becomes the expectation value of this beta I object of x prime. OK, so this is sort of the key result. And I'm just showing you sort of mechanically in a calculation. You just do the derivatives. You see the sum that appears. And you see that you can reinterpret it in the limit by the law of large numbers as an average. And now this average is computed over all the distributions of all of the parameters of this object. And you can just see if you can evaluate that integral. And if you can, you just have well, it's fixed regardless of whether you can evaluate the integral. But it's nice to have integrated functions rather than representing them as an integral. And for a bunch of networks, you can just compute it. Rikab.
What are A and B?
Yes, very good. I switched my notation. This is how I normally think of it. So this is W0I. Sorry, A is W1, my bad. WI1. And this thing that I was calling B is W0. I was writing this down last night and took my normal notation and imposed it here. Apologies. Yeah. Good? Yeah. Can someone DM me on Slack to shore up this equation in my notes? There's a couple of typos. OK. So that's the point. This is just some calculation in some simple setup. You can write this down as an integral over parameters, and you can just try to compute it. And in some cases, you can. And you just know what it is. So this that I'm showing you here is this nice 2 fact applied in an example. Okay.
I have a question. So,
Sure.
why does the set of parameters take x and x prime as arguments? Wouldn't that mean that
This is a capital theta.
Oh, okay.
Yeah, a capital theta. Yeah, I'm trying to always write capital.
To me, it looks like a little TIE fighter.
That's good. Yeah, it does look like a little TIE fighter. The NTK is often written as capital theta, and parameters are often written as lowercase theta. So I'm trying throughout to write them capitally enough. So sorry about that. OK, other questions? OK, I'll erase while you come up with brilliant questions. All of the dynamics, this entire lecture is gradient descent. Good. I'm in part 2 now. Was there another question? Let me, OK, so massive simplification because theta bar is a nice object. That's a Diffie-Q, yeah? Diffie-Qs can sometimes be solved, but whether it can be solved or not depends on dl by d phi. So it depends on what loss function you choose. Does anyone have a favorite loss function? Yes, good. Mean square error loss. There's all these loss functions, but we're going to do mean square error. Good. So this is an exactly solvable model. L of phi of x. So I'm making a choice here. Is the mean squared error loss? Yeah? Does anyone know the functional derivative of this? It's just linear. So I'm going to end up in a situation where my dynamics now, because I take dl by d phi, my dynamics now alpha there's the targets. Nice. That looks like something that we can solve. And the solution is that phi of x, I think I can do this all here, maybe. Let me give myself a little room. Phi t of x. I forget where I originally solved this first. The paper that I normally go to that I copied and slightly modified the equation from is called Wide Neural Networks of Any Depth Evolve as Linear Models Under Gradient Descent. It's a famous paper out of the Google team from 2019. Love that paper. Good. So the solution is phi 0 of x plus 1 over d theta bar. I'll write it big. I'm going to have to go to the next line. Theta bar of x alpha, theta inverse bar x alpha. I'll write it up here, the inverse times 1, the identity matrix, minus e to the minus eta theta bar. This is theta bar evaluated on train data. I'm going to give it train data indices, beta gamma. Y gamma minus phi 0 x gamma. OK. So that is the solution to this ODE. It is defining a trajectory through function space. Good, let's sanity check. I plug in t equals 0. This thing is 1 minus 1, which is well known to be 0. And I'm just left with this thing left over. So the labeling of phi 0 of x is correct. It starts its life here. And as t goes on, it starts picking up corrections to the function that are coming through this kernel here. And I'd like to point out in particular, I know it for all t. And therefore, I also know what it becomes at time equals infinity. OK. So that's cool. In this setup, you can write this. This is if you trained your infinitely wide neural network to infinite time in a supervised setting with some NTK, this is the function that you would get. And this is what you would get from training. But in principle, you just know this function now, and you don't have to put it on a computer. This is known as kernel regression. It's a type of known technique in ML. So generally, one chooses the kernel. This is the kernel. Gosh, sorry, I forgot one.
Alpha and beta indices, are they supposed to both be beta?
Yeah, there's an extra term here that's missing. Plus theta bar x alpha, theta bar inverse x alpha, x beta. Good. So beta, beta, alpha, alpha, x. Yeah, thank you. I was missing a term. So this is called kernel regression. In general, in kernel regression, you pick a kernel, like a Gaussian or something else. The kernel is this thing that's doing the interpolation between the trained data and the test data. Here, it's a particular kernel that arises. And if you go to the first neural tangent kernel paper, the abstract says something like, we show that in an infinite width limit, certain neural networks have gradient descent dynamics that are equivalent to kernel regression with a particular kernel, the neural tangent kernel. OK, so this is something where we know what's happening. We know an analytic solution at time infinity. And I'd point out that on train points, we have something that is called memorization. So let us pick some train point here. What we can see is that phi of x gamma is equal to, I don't have a gamma anymore, so I can do that, is equal to y gamma for all gamma. So this is some test point, but if I put a particular gamma in there that is, I'm missing something. Yeah, good. So the theta 0 piece is dropping out when you take 1 to be a train point here. And in particular, this is an inverse matrix appearing here. And this object will become 1, in this limit, it'll become 1 gamma beta. Yeah. And so it perfectly memorizes the training data. The network perfectly predicts what the label is, but that's only on train data. And something you probably learned from Christoph and last week, and maybe in other cases, is that we don't just want the network to do well on train data, we also want it to generalize to test data to data it hasn't seen. So it's memorized the training data, but the downside is that it is making predictions for the test data, even though it's very good on train data, that is some sort of interpolation, some sort of kernel regression with some fixed kernel that has nothing to do with the neural network learning. It just has to do with the neural network at initialization. So we see the upside, it memorizes training data. That's what the kernel regression is doing. But the downside is that on test, it's not, in general, we shouldn't expect it to generalize well because it's not actually learning some evolving kernel. It's a fixed kernel once and for all. Yes?
Isn't this another way to say that we are reaching overfitting?
Yeah, you could put it that way, but really the question of whether it overfits is the question is it overfitting? Overfitting is a phenomenon where there is a huge discrepancy between your train error and your test error. There is 0 train error in this model. It memorizes perfectly. So whether it really overfits or not is a function of just how bad the test error is, which is a question of just how good or bad is this kernel at interpolating between test and train data. People use kernel regression, and in many settings it works. I just listened to this audiobook, The Man Who Solved the Market, about Jim Simons. And apparently, in the 80s, early on in his investing days, they were using kernel regression to make various market predictions, and he was complaining that it was a black box or something like that. But people do use kernels in real-world settings, and sometimes for certain kernels that are wisely chosen, it can do it can generalize somewhat well. But for an arbitrary kernel, the difference between the train and test error is going to be enormous, and it will have overfit. Absolutely. Yeah.
I have a question about the.
Sure.
About the theta bar being about the same as its initial value, but wouldn't that also apply to the? Sorry, another thing. The gradient or the del of x equals to the gradient of the loss function.
Sorry, can you state the question concisely? I'm missing it.
Sine base phi is just equal to its initial value in the lazy regime. Wouldn't that mean that delta of x alpha is also about equal to its initial value in that regime for a non-unusual loss function? Does that mean that the theta of dt is just a constant, just evolves linearly?
No, you can show that it's not. Right, you can show that it's not a constant because I have this exact solution that shows the time dependence. But you're asking the question sort of how do I understand the size of this object relative to that in 1 over n or something like that.
Yeah, or how much they're changing.
Yeah, I forget the answer to that. It's a good question. I'm sorry I can't answer it. OK, I have one more comment on this solvable toy model, and then I need to go on to feature learning. And I only have so many minutes left. OK, so I want to make one more point. that with this exact solution, I promised you at some point, so I could ask the question, this is the prediction, and it depends on the initial value of the neural network. Can I average over the neural networks and over this space of solutions? So what I'm going to do is I'm going to take mu infinity of x to be the average of phi infinity of x. And what happens if you're in a situation which is pretty common where the 1-point function vanishes, the expectation value of this is 0. So like if the output weights have 0 mean, the 1-point function vanishes. I'm in that case. And then in that case, this equation just becomes this. OK, good. And we have some, OK, this is something that's important. And we have some remarkable facts that I think are remarkable. So what this object is, mu infinity of x is the mean prediction of an infinite number of infinitely wide neural networks, or infinitely large, depending on the context, trained to infinite time. OK. I said infinity too many times. I shouldn't be able to do that, right? In particular, you can't fit a single infinitely wide neural network concretely onto a computer because there's too much information and it'll turn into a black hole. OK? So that's not how you do it. You cannot train an infinitely wide neural network concretely on a computer with an infinite number of parameters. Obviously, your RAM isn't good enough. OK? Instead, this is a true fact that this is the mean prediction of an infinite number of infinite wide neural networks trained to infinite time. The reason we can do this is because a different duality frame opened up. That's, I think, the way we should say it. There's a different description of the theory that simplifies in this limit. Literally putting this infinitely wide neural network on a computer and trying to train it is not only a terrible idea, it's impossible. But in this limit, there's a simplification that opens up a different description of the theory, and we end up with an analytic solution. So this is remarkable thing number one. Slightly remarkable, but slightly less remarkable, is that if phi 0 is drawn from a GP, a Gaussian process, then phi t is as well for all t. GP, not GD. Yes, GP. So if phi is Gaussian, if the distribution of neural networks is Gaussian at initialization, as you follow this trajectory will move the distribution on function space as a function of time. It stays Gaussian the entire way. So this is a case where you not only know the mean prediction of the infinite number of infinitely wide neural networks trained to infinite time. Analytically, it's in the Google paper and maybe even in the original paper. You also know the covariance. And the mean and the covariance are all there are because it's Gaussian for all times. OK. Good. That is all I wanted to say about NTK and the solvable model. We already talked about ways in which we think this might be bad, in the sense that the thing that is interpolating is a fixed function. Okay? But even though there's that downside, these things are true in these models. So this is a toy model that's interesting for a number of reasons. Anyone else?
So can you use this to say anything about how that validation data that's not in the training would relate to your distribution of bias?
So the question is, can you say something? Can you repeat it one more time? I think I didn't get it.
I'm wondering about validation data, because this is
Yeah.
sort of, this always has the feature of memorization.
Yes.
What will differ as you vary the phi naught distribution will be
Yes.
response to out of sample data.
Good. Yes. I'm sorry. I understand now. Ethan's question is, can you talk about the statistics of the test data, the predictions on test or on validation? And the answer is yes. Memorization here, it's memorization for all the networks. Memorization means on train that there's no variance in the infinite time predictions. What the covariance function that's in the Google paper lets you do is exactly characterize the variance of the test set predictions. So you know the variance of the test set distribution as well, and also the mean. So yes, it's known. And in particular, like if you're someone who loves jets, but your tagger is giving huge variance in its predictions, and in this case, you could actually compute and analyze the variance of those predictions, Granted, you're not using MSE loss, but anyways, that is a problem. And so the statistics of the test predictions are also known. Cool. Good. All right, let me tell you the feature learning result. The derivation is way too long. It's not that long. Like, I, in principle, could have done it, but your questions are too good. So, in essence, what happens here is that the n scaling that's chosen is such that it shuts off feature learning. Okay. And so the question that people like to ask is there better scaling with respect to hyperparameters that gives rise to non-trivial feature learning? And here I will just try to write things down carefully, tell you the concepts, and then tell you the results of the derivations from the concepts. So now I'm going to take a deep network, and I'm going to have phi of x is 1 on gamma 0. I should say thanks to Cengiz and Blake for writing beautiful Princeton lecture notes last year at the ML school there. I am definitely pulling from them. And honestly, their derivation clarified this for me, too. OK. This is ZL of x. ZL of x is 1 over n to the AL. AL and these A, B, and C parameters that you're going to see appearing are hyperparameters that govern the n scaling. So we're wanting to study how, as we scale the size of the network n, which here is the width, how do these things change? We're going to parameterize our ignorance. That's the last layer. So here, the superscripts, the depth is L of the network. So I have a width parameter n. I have this depth parameter. So like the number of compositions is L. This is the last layer. At an intermediate layer, at the Lth intermediate layer, these Z's are called pre-activations. I'll try to write this down faithfully and then explain it. These Z's are called pre-activations because they're pre the activation. Yeah, OK. And Z1, finally, 1. And A1, root D. Here, his dimension of his input is capital D, following his convention. Xj. Good. I'll write down the weights also. So the weight distributions here are, for simplicity, taken to be Gaussian. You can muck with that a little bit if you so choose. OK. 1 over n to the b, L. And finally, eta is some, there are these parameters that are appearing, n to the 2d minus c. Let me say something. OK, so this is my input to the neural network. It comes in through the first layer, and it gives me the first pre-activation. The first pre-activation would go into the L equals 2 version of this. It would come in here, get hit by a sigma, multiplied by a w, scaled by an n. That gives me the next pre-activation. I do it again and again and again. This is how deep neural networks work. I don't only have a hyperparameter n that is the dimensionality of this index. I have a depth L, which is the number of compositions I have. So I can make the network deep. This is deep learning, not just shallow learning. OK? But I'm not sure. I think this might originally be due to my friend Greg Yang. He has something that he calls the ABC parameterization, which is basically related to these A's and B's and C's appearing here. The n scaling in these setups is very clearly left in terms of parameters. And what we're going to have is we're going to have principles of things we want to be true of the learning process. And then given those principles, there's calculations that are in the notes that I'm not going to do because I have 15 minutes. And those principles are going to fix the parameters. So we're trying to parameterize our ignorance in the n scaling, and then we're going to demand that learning is sufficiently nice, and then it's going to fix things, OK? And that's the setup. Questions on that?
So for these expectation or distributions
Yes.
for the W's, why is there a B, so capital L on the WL, or the B and
Yep, thank you. That is a, I appreciate that. This is only in the last layer here. You're absolutely right. It's a capital L. Yeah.
what about the other?
This is just for the last layer. These W's are all matrices for all the intermediate layers. And so this L runs from 1 all the way up to the last thing. The last thing is called capital L. And this is the thing that contracts me to a scalar. So this L is the index that runs from 1 to capital L, because I have L compositions. And so this is true. Good, I should write that. L equals 1 to, I guess, L minus 1, up to the last layer. Yes? Here?
Yeah.
That's BL and B little l. This is AL, AL, A. So the A's are the things that are governing the n scaling of the pre-activations. The B's are the things that are governing the n scaling of the variances of the weights. There's this D here that is appearing here, and this D also appears in the learning rate, and there's one more parameter C that appears in the learning rate. It's just trying to parameterize your ignorance about the n scaling so that you can make demands and hope that they're satisfied. Cool. OK, let me tell you about the demands and the result. I encourage you to look at the calculations. Give myself 2 boards. If there are questions, let me know. I can take them while I erase. Yes, this is why he calls it capital D, because this D that appears here, here in the setup in this derivation, phi is a map from R capital D to R. So that D is that D, and this is a parameter that governs the n scaling. Yep. This was exactly the thing that I had to do and ask myself as I was going through the derivation. Yeah. OK, so let's just talk about concepts. So we want 3 things. OK, and we'll use this freedom in these parameters to meet some reasonable goals. We want finite pre-activations. So ZL, we want to go like order n1. So this is like n to the 0 for all L, including the last layer. You probably don't want what's happening in your neural network to diverge as you make the model big, as you crank up n. You probably also don't want it to die down to 0. So we want it order 1 in n. The other thing that you want is learning in finite time. By that, I mean that the predictions of the neural network, the updates to the neural network, d phi by dt, that these are also order 1 in n. OK, so if your predictions went as n to some power and you made n infinite, your predictions are diverging. If it goes like n to the negative power, they're becoming all 0 as n goes to infinity. And then also feature learning in finite time. So this is the constraint that these dz's by dt is order 1 in n. Okay. So this is basically just saying we want the n dependence of this system to be such that nothing too sick happens. We want sort of everything. We want the feature evolution and the prediction evolution and the features themselves, the ZLs, also known as the pre-activations. We want everything to be order n to the 0, so that as I change n, things don't get sick. Okay. And good. If you also demand, not everyone does this, that the learning rate is order 1 in n, then this is unique. So there's with just these three, there's a 1 parameter family of solutions. The details are given in the notes. The details don't matter. All you need to know is what I mean by solutions. I mean you do the calculations for each one of these things. You see how the A's, B's, C's, and D's have to scale to satisfy all of these things. And there's a 1 parameter family of solutions to have everything be well behaved to meet these goals. If you also fix this, then if you also have this also, then it's completely fixed, and there's one solution. And it's called the maximal update parameterization, or mu p. Also known as mu p. I think it's because if you write \mu in LaTeX, MUP, maximal update, or just mu p, MUP, maximal update parameterization, or mu p. But this is, there's a couple of good theories out there of feature learning. There's probably a lot more than I know. A lot of them are by physicists and mathematicians-oriented people, people with degrees in the sorts of things that we do. And this is a pretty reasonable set of things here. I should say that getting this one to work, good, let me say this. I'll put this up. I'll say this. So after fixing, the first two are solved. Feature learning, the third one, requires d equals 1/2. Okay, it's a fact. You can do the calculation. And the NTK corresponds to d equals 0. And for d less than 1/2, what you find is that the n scaling is such that the features aren't updating anymore as n goes to infinity. So there's no feature learning for d less than 1/2. OK. I have 5 minutes. I got to where I wanted to be. I was going to say some things about field theory more generally, but this maybe is a good spot to end in. I'll answer whatever questions you have. The punchline of the lecture is that I presented 2 of the essential ML theory results from the last 10 years. One is about a very nice limit where feature learning doesn't occur, and there's just this, there's memorization of the train data, but the test predictions are all just this interpolation thing. And then if you make these demands, you end up with a unique solution called the maximal update parameterization. And this is the thing that can let you scale up your network and not have to change hyperparameters so much. So this is what I mentioned my friend uses for large language models. Yes?
So what is the precise definition of feature learning? I mean, why should I associate that with generalization on the test set?
Good. That's sort of a different question, generalization on a test set. Sort of the definition of features here is like the things that are learned in the extra dimensions. Sometimes people define the features just to be the last embedding layer, so the pre-activations in the last layer. Here we're sort of defining it as anything that happens in the deep network, any of these ZLs that get turned on. And the notion of learning here is basically that they're just updating in a non-trivial way. You can definitely some people take issues with the words that are used, but whatever it is that's happening, we're hoping that our neural networks learn meaningful representations at intermediate layers that capture the correlations in the data in a meaningful way. And so to be able to do that, you need DZL by DT to move around a little bit. You need to be able to have the pre-activations update. So that's the sense in which the features are learning. Yeah?
In that exact case of the
Yes?
instead of gradient descent, if you use stochastic gradient descent, do you think dynamics would change?
Yes. So the question is, what if you do stochastic gradient descent instead of gradient descent in the exactly solvable model? Yes, because there's noise that comes into the game, and you have to solve a stochastic differential equation instead of a normal, ordinary differential equation. Stochastic gradient descent basically says, instead of at every epoch training on all of my data, I'm going to pick a subset of the data to train on, and in fact, I'm going to pick different subsets every epoch. And so it's not always backpropagating through the same data. It's backpropagating losses from different data at each epoch.
So is there any feature flag to
I'm not so familiar with all of the literature along those lines. I'm pretty sure there are papers out there that do SGD versions of NTK. I don't remember their results. It's a great question. Yeah?
Somewhat inspired by biology, I was thinking that in neural networks, one can imagine some sort of pruning in which some areas of the neural network just turn off.
Yes.
So the first finite reactivation of all the one, isn't it forcing that all the parts of the neurons are active, and so preventing from these pruning activities?
What it means is that if there is shutting off, it's not happening just to some dumb end-dependent effect. So one thing that is really bad for learning that you're getting at is you could say, I'm going to choose my end scaling such that it literally shuts off all of the connections between layer 1 and layer 2, for instance. In that case, you're turning off all the weights, and the pruning is like giving you a disconnected network, which is not going to learn at all. Pruning generally is a major subject, and it's important and something I've been thinking about recently. But in some sense, at least at the level, this is guaranteeing that there's no N effect that is forcing this complete cutting of the network. Because if it was going like 1 over n to some power and you made it big, it would literally just be shutting off all the weights and they can't update. You get this disconnected network. Yeah. Yes? I think it already is. I think a package was written, I think maybe even Greg wrote it. Good, the question was ultimately, is there an implementation of μp out there? And the answer to that is yes. I think there's a PyTorch version. I don't know if it'll be in the default PyTorch setup. Maybe. I don't know how that has really evolved. I remember when this result came out and related results in the literature, Dan Roberts and Sho Yaida have a beautiful book along similar but slightly different lines. Cengiz and company do similar sort of stuff, slightly different lines. I haven't really followed how the implementations have evolved, but I'm pretty sure there are implementations. And for μp, I'm certain there's an implementation. I think it's just not PyTorch default. Yeah. Other questions? Okay. This is a very field theory way of thinking about ML and some flow in some distribution on functions where the flow is governed by learning. Thanks a lot.
Thanks, Jim, again for a wonderful lecture.
Thanks a lot.